Deep in the darkness beyond Neptune, where sunlight barely whispers and the cold reaches depths that would make Antarctica feel tropical, astronomers have stumbled upon something extraordinary. A cosmic wanderer they've nicknamed Ammonite, drifting in the outer reaches of our solar system like an ancient ghost from the dawn of time. But this isn't just another space rock floating in the void. This discovery might just unravel one of astronomy's most compelling mysteries and send a beloved theory tumbling into the cosmic dustbin. Real quick, can you drop a comment and tell us where in the universe you're watching from? We love to meet new explorers. Picture this. You're an astronomer peering through one of the most powerful telescopes on Earth, scanning the heavens night after night, looking for objects so distant they take decades to complete a single orbit around our sun. Most of what you find follows predictable patterns, well-behaved cosmic citizens that dance to the gravitational tune of the giant planets. But every so often, you spot something that breaks all the rules, something that shouldn't exist where it is, moving the way it does, defying easy explanation like a rebellious teenager, thumbing their nose at the laws of physics. That's exactly what happened when researchers using Japan's Subaru telescope first caught sight of Ammonite in March of 2023. Officially designated 2023 KQ-14, this mysterious object sits in one of the most desolate neighborhoods in our solar system, somewhere between 66 and 252 astronomical units from the Sun. To put that in perspective, when Earth is having a lovely summer day, Ammonite is so far away that our Sun appears as nothing more than a bright star in its sky, providing less warmth than a birthday candle held at arm's length. But distance isn't what makes Ammonite special. It's the company it keeps and the rules it refuses to follow. You see, Ammonite belongs to an exclusive club of cosmic oddballs called Sednoids, named after the first member discovered, a dwarf planet called Sedna. These are objects that follow such extreme, elongated orbits they spend most of their time in the outer darkness, only occasionally swooping closer to the Sun before heading back into the cosmic wilderness for thousands of years. Before Ammonite crashed the party, there were only 3 known Sednoids. Sedna itself, discovered in 2003, takes roughly 11,400 years to complete one orbit. Then there's 2012 VP-113, found nearly a decade later, and Lelikuhanua, discovered in 2018. Each of these objects follows a path so stretched and distant that even at their closest approach to the Sun, they remain far beyond the gravitational influence of Neptune, our solar system's outermost giant planet. Now here's where things get interesting. And by interesting, I mean astronomically puzzling in the best possible way. When scientists plotted the orbits of these first 3 Sednoids, they noticed something remarkable. Despite being scattered across the outer solar system, their orbits seem to be aligned in a similar direction, clustered together like cosmic sheep following an invisible shepherd. This wasn't supposed to happen. Random gravitational interactions with the giant planets should have scattered these objects in all directions, yet there they were, marching in formation across the darkness. This mysterious alignment sparked one of the most captivating theories in modern astronomy, the Planet 9 hypothesis. Back in 2016, 2 astronomers from the California Institute of Technology, Konstantin Batygin and Mike Brown, proposed a radical explanation for this clustering. What if, they suggested, there's a massive undiscovered planet lurking in the outer reaches of our solar system? A world perhaps 5 to 10 times more massive than Earth, orbiting 20 to 30 times farther from the Sun than Neptune, completing one orbit every 10 to 20,000 years. This hypothetical Planet 9, they argued, could be the invisible shepherd responsible for herding these distant objects into their aligned orbits. Its gravitational influence, subtle but persistent over billions of years, could explain why objects like Sedna, 2012, VP-113 and Lelekuhanua all seem to follow similar paths through space. It was an elegant solution to a cosmic puzzle, the kind of theory that makes astronomers' hearts race with excitement. The idea of Planet 9 captured imaginations worldwide. Here was a world hiding in plain sight, or rather, hiding in the cosmic darkness just beyond our ability to detect it directly. Scientists began modelling its potential orbit, estimating its size, and planning searches to finally spot this elusive giant. The prospect of discovering a new planet in our own solar system, the first since Pluto's discovery in 1930, was intoxicating. But science has a way of keeping us humble, and the universe delights in confounding our most cherished theories. Enter Ammonite, stage left, carrying what might be a death sentence for the Planet 9 hypothesis. Unlike its three Sednoid siblings, Ammonite doesn't play by the same rules. When astronomers calculated its orbit and compared it to the expected patterns from Planet 9's influence, something was wrong. Ammonite's path doesn't align with the supposed direction of this hidden planet's gravitational pull. In fact, computer simulations suggest that if Planet 9 exists where scientists think it should, Ammonite would likely have been ejected from the solar system entirely, flung into interstellar space like a cosmic slingshot victim. This misalignment is more than just a minor inconvenience for Planet 9 supporters. It's a fundamental challenge to the theory's core predictions. If a massive planet is really out there shepherding objects into aligned orbits, then every member of the Sednoid family should show signs of its influence. Ammonite's rebellious trajectory suggests either Planet 9 doesn't exist at all, or it's located somewhere completely different from where astronomers have been looking. The discovery of Ammonite emerged from a project with the wonderfully acronymic name FOSSIL, which stands for Formation of the Outer Solar System, an icy legacy. Led by an international team primarily from Japan and Taiwan, this survey uses the Hypersuprime Cam on the Subaru telescope, one of the most powerful wide-field cameras on Earth, to scan the outer reaches of our solar system for exactly these kinds of mysterious objects. The Subaru telescope, perched atop Hawaii's Mauna Kea volcano, is uniquely suited for this cosmic archaeology. Its massive mirror and sensitive instruments can detect objects so faint and distant that they appear as mere specks of light moving slowly against the background stars. Finding something like Ammonite requires incredible patience, comparing images taken months apart to spot the subtle motion that betrays the presence of a distant world. What makes Ammonite's discovery even more impressive is that astronomers managed to trace its history back through nearly 2 decades of archived observations. After confirming its existence with follow-up observations from the Canada-France-Hawaii telescope in 2024, researchers dug through old data from various observatories and found images of Ammonite dating back to 2005. This extended baseline allowed them to calculate its orbit with remarkable precision, revealing the full scope of its cosmic journey. Ammonite follows an elliptical path that takes it from about 66 astronomical units at its closest approach to the Sun, out to roughly 252 astronomical units at its most distant point. To appreciate these distances, consider that Neptune, our solar system's outermost giant planet, orbits at about 30 astronomical units from the Sun. Even at its closest, Ammonite remains more than twice as far from the Sun as Neptune, dwelling in a realm of perpetual twilight where temperatures hover around negative 230 degrees Celsius. The object itself is estimated to be between 220 and 380 kilometers in diameter, roughly the size of a small asteroid or perhaps large enough to qualify as a dwarf planet. At such vast distances, determining the exact size requires careful analysis of how much sunlight the object reflects, combined with assumptions about the darkness of its surface. Most objects in the outer solar system are quite dark, coated with organic compounds that have been baked by cosmic radiation over billions of years, giving them the reflective properties of charcoal. But size and distance are just the beginning of Ammonite's story. Computer simulations suggest this object has maintained a stable orbit for at least 4.5 billion years, making it nearly as old as the solar system itself. This incredible stability indicates that Ammonite is a genuine fossil from the early days of planetary formation, a survivor from an era when our solar system was a chaotic construction zone filled with colliding planetesimals and migrating giant planets. The implications of this ancient stability are profound. If Ammonite has been following essentially the same orbit for billions of years, it means whatever forces shaped its path operated during the solar system's youth, not recently. This temporal constraint adds another layer of complexity to theories about how these extreme objects acquired their unusual orbits. Dr. Fumi Yoshida, one of the researchers involved in Ammonite's discovery, notes that the object was found in a region so distant that Neptune's gravity has virtually no influence on its motion. The presence of objects with such elongated orbits and large perihelion distances in this area implies that something extraordinary occurred during the ancient era when Ammonite formed. Understanding the orbital evolution and physical properties of these unique, distant objects is crucial for comprehending the full history of our solar system. The Discovery team's computer simulations reveal another intriguing detail about the Sednoid family. Approximately 4.2 billion years ago, the orbits of all known Sednoids, including Ammonite, were remarkably similar. This primordial alignment suggests that whatever mechanism created these extreme orbits operated during a specific period in the early solar system, perhaps during the final stages of planetary formation or shortly thereafter. This ancient clustering raises fascinating questions about what could have caused such a dramatic reorganization of the outer solar system. Various theories have been proposed, ranging from close encounters with passing stars to the presence of additional planets that were later ejected from the solar system entirely. Each scenario would leave different fingerprints on the population of surviving objects, and Ammonite provides a crucial new data point for testing these competing hypotheses. The story of how Sednoids like Ammonite came to exist reads like a cosmic epic of survival against impossible odds. During the solar system's early years, the region where these objects now reside was likely much more crowded, filled with countless icy bodies and rocky fragments left over from planetary formation. The gravitational dance of the giant planets, particularly Jupiter and Saturn, would have stirred this primordial population, flinging most objects either inward toward the Sun or outward into interstellar space. Only a tiny fraction of the original population survived this gravitational purge, and those that did were sculpted into the extreme orbits we observe today. The survivors, including Ammonites, became cosmic time capsules, preserving information about conditions in the early solar system that would otherwise be lost forever. The process of discovering and studying these ancient wanderers requires a level of patience that would make a monk envious. Unlike planets or asteroids that zip around their orbits in years or decades, Sednoids move with glacial slowness across the sky. From Earth's perspective, they crawl against the background stars like cosmic snails, shifting position by mere fractions of an arc-second from night to night. This sluggish motion is both a blessing and a curse for astronomers. While it makes these objects incredibly difficult to spot initially, once found, their predictable paths allow researchers to trace their movements across decades of archived observations. The challenge of detecting something like Ammonite cannot be overstated. Imagine trying to spot a piece of charcoal the size of a city block sitting in complete darkness, illuminated only by a flashlight held several football fields away. That's essentially what astronomers accomplished when they first identified this distant wanderer. The fact that we can detect and study such objects at all represents a triumph of modern technology and human persistence. The Fossil Project represents exactly this kind of systematic persistence. Rather than randomly scanning the sky hoping to stumble upon interesting objects, the survey methodically covers specific regions where theory predicts these ancient survivors might lurk. The team uses sophisticated algorithms to compare images taken at different times, automatically flagging anything that moves against the stellar background. It's like having a cosmic motion detector, sifting through millions of stars to find the handful of objects creeping slowly across the void. This systematic approach has revealed something unexpected about the outer solar system. Far from being empty space punctuated by the occasional lonely rock, the region beyond Neptune appears to harbour a surprisingly rich population of these ancient objects. Current estimates suggest there could be dozens, perhaps hundreds, of Sednoid-sized bodies waiting to be discovered in the cosmic darkness. Each new find adds another piece to the puzzle of our solar system's violent youth. But Ammonite's discovery does more than just add to the census of distant objects. It fundamentally challenges our understanding of how these extreme orbits came to exist in the first place. The Planet 9 hypothesis relies on the idea that all Sednoids should show similar orbital alignments, evidence of being shepherded by a single massive perturber. Ammonite's contrarian orbit suggests the story might be more complicated than a simple case of planetary herding. Consider the gravitational dynamics at play here. If Planet 9 exists as theorized, it would need to maintain its influence over billions of years, while the Sednoids complete thousands of orbital cycles. During each orbit, these objects would feel the subtle tug of the distant planet, gradually adjusting their paths in response to its gravitational whispers. Over cosmic time, this influence should produce a clear signature in the orbital distribution of all affected objects. The fact that Ammonite doesn't fit this pattern suggests several possibilities, none of them particularly comfortable for Planet 9 proponents. Perhaps the hypothetical planet is located much farther away than originally thought, weakening its influence to the point where some objects escape its gravitational embrace. Or maybe Planet 9's orbit is significantly different from theoretical predictions, creating a more complex pattern of influence that doesn't affect all Sednoids equally. More troubling for the theory is the possibility that Planet 9 doesn't exist at all, and the apparent clustering of the first three Sednoids is simply a cosmic coincidence. With only a small sample of these objects known, it's entirely possible that what appeared to be meaningful alignment was just the result of observational bias or statistical bad luck. Ammonite's discovery begins to test this possibility by expanding the sample size and revealing whether the clustering holds up under scrutiny. The debate surrounding Planet 9 reflects a broader challenge in astronomy. How do you prove the existence of something you can't directly observe? Unlike exoplanets, which occasionally transit in front of their host stars or gravitationally wobble their suns, Planet 9 would be far too faint and distant for direct detection with current technology. Instead, astronomers must rely on circumstantial evidence, inferring the planet's presence from its supposed effects on other objects. This indirect approach makes the theory particularly vulnerable to new discoveries that don't fit the expected pattern. Each additional Sednoid found either strengthens the case by showing the predicted orbital alignment, or weakens it by revealing objects that march to their own gravitational drummer. Ammonite appears to fall firmly in the latter category, its rebellious orbit casting doubt on the neat theoretical framework that Planet 9 was meant to provide. Alternative explanations for Sednoid formation have gained renewed attention in light of Ammonite's discovery. One intriguing possibility involves rogue planets, massive worlds that were ejected from the solar system during its chaotic youth. Computer simulations suggest that such a planet could scatter objects into extreme orbits before being flung into interstellar space, leaving behind a population of survivors with diverse orbital orientations. Another scenario invokes close encounters with passing stars during the Sun's early years. Our solar system didn't form in isolation, but rather within a crowded stellar nursery where neighbouring stars could approach close enough to gravitationally stir the outer regions of the developing planetary system. Such encounters could lift objects from circular orbits into the elongated paths we observe today, creating the Sednoid population through stellar rather than planetary influences. The stellar encounter hypothesis has particular appeal because it naturally explains the diversity of Sednoid orbits. Unlike the Planet 9 scenario, which predicts similar alignments for all affected objects, stellar flybys would create a more random distribution of orbital orientations. Each passing star would affect objects differently depending on their location and orbital phase during the encounter, producing the kind of mixed population that Ammonite seems to represent. Recent research has also explored the possibility that multiple mechanisms operated simultaneously during the early solar system's evolution. Perhaps some Sednoids were shaped by planetary influences, while others resulted from stellar encounters or the ejection of rogue planets. This multi-mechanism approach could explain why objects like Sedna, 2012 VP113, and Leleaka Honua show orbital clustering while Ammonite follows its own path. The timing of these various processes adds another layer of complexity to the puzzle. Computer simulations suggest that the current orbits of all known Sednoids converged to similar orientations roughly 4.2 billion years ago, during what researchers call the Primordial alignment. This ancient clustering occurred during a critical period in solar system evolution, shortly after the giant planets had settled into their current positions, but while the outer regions still contained significant populations of leftover planetesimals. Understanding this primordial alignment requires careful analysis of how different formation mechanisms would affect orbital evolution over billions of years. Some processes, like the gradual influence of a distant planet, would maintain orbital clustering throughout cosmic history. Others, such as stellar encounters or planetary ejections, might create temporary alignments that would gradually disperse over time. The fact that Sednoid orbits appear to have been more tightly clustered in the past than they are today provides important clues about which mechanisms were actually at work. The implications extend beyond just understanding these particular objects. Sednoids, like Ammonite, serve as cosmic archaeology artifacts, preserving information about conditions during the solar system's most violent and transformative period. Their orbits record the gravitational chaos that accompanied planetary formation, migration, and the eventual stabilization of the configuration we see today. This archaeological perspective makes each new Sednoid discovery precious beyond its immediate scientific value. These objects are survivors of processes that destroyed the vast majority of their contemporaries, leaving only scattered witnesses to testify about events that occurred billions of years ago. Ammonite's story, written in the mathematics of its orbital elements, provides testimony about forces and events that would otherwise remain forever hidden in the deep past. The technical challenges of studying such distant objects continue to push the boundaries of astronomical capability. Current surveys can detect Sednoids only when they're relatively close to the Sun, during the brief portions of their orbits when reflected sunlight makes them barely visible against the cosmic background. This observational bias means we're seeing only a fraction of the total population, like trying to understand a city's demographics by observing only the people who occasionally visit the downtown area. Future telescopes promise to expand our view of this distant population dramatically. The Vera Rubin Observatory, currently under construction in Chile, will conduct the most comprehensive survey of the southern sky ever attempted, potentially discovering hundreds of new trans-Neptunian objects, including many additional Sednoids. This flood of new data will either vindicate or demolish theories about Planet 9 and the formation of extreme orbits. The anticipation surrounding these future discoveries reflects the high stakes involved in understanding our solar system's architecture. If Planet 9 exists, its discovery would represent one of the most significant astronomical finds in modern history, adding a new world to our cosmic neighborhood and validating decades of theoretical work. If it doesn't exist, astronomers will need to develop entirely new explanations for the observed population of extreme objects, potentially revolutionizing our understanding of planetary system evolution. Meanwhile, Ammonite continues its ancient journey through the outer darkness, oblivious to the scientific controversy its discovery has sparked. Every few hundred years it reaches the innermost point of its orbit, briefly basking in slightly more sunlight before heading back into the cosmic wilderness for centuries more of frozen solitude. Its next close approach won't occur for generations, but its legacy in reshaping our understanding of the solar system's most distant reaches has already begun. The dance between theory and observation in astronomy resembles a cosmic waltz where partners occasionally step on each other's toes. For years, Planet 9 proponents have maintained their confidence despite mounting challenges, adjusting their theoretical choreography with each new discovery that doesn't quite fit the expected pattern. But Ammonite's arrival on the scene feels different, like a dancer who's suddenly changed the music entirely. Dr. Konstantin Batygin, one of Planet 9's original champions, remains cautiously optimistic despite Ammonite's orbital rebellion. He suggests that the hypothetical planet might be located much farther away than initially predicted, weakening its gravitational influence to the point where objects like Ammonite could escape its shepherding effects. It's a bit like arguing that the invisible dog walker is standing much farther back, allowing some cosmic pets to wander off the gravitational leash while others remain obediently clustered. This adjustment, while theoretically possible, comes with its own set of problems. The farther Planet 9 sits from the Sun, the weaker its gravitational influence becomes, and at some point it would be too distant to explain the clustering of the other three Sednoids that started this whole theoretical adventure in the first place. It's a delicate balancing act, trying to position an invisible planet far enough away to explain Ammonite's independence, while keeping it close enough to maintain its supposed influence over Sedna, 2012, Vihi-113, and Leleaku Honua. Alternative theories have begun to emerge from the shadows, each offering different explanations for how these cosmic outcasts acquired their extreme orbits. One particularly intriguing scenario involves what astronomers poetically call stellar nursery chaos. Our Sun didn't form in splendid isolation, but rather within a crowded cluster of newborn stars, all jostling for position like cosmic teenagers at a particularly energetic dance party. During this early period, neighbouring stars could have approached close enough to gravitationally stir the outer regions of our developing solar system. Imagine a massive star wandering within a few hundred astronomical units of the young Sun, its gravity reaching out like invisible fingers to pluck objects from their original orbits and fling them into the extreme paths we observe today. Such stellar encounters would naturally produce a diverse population of orbital orientations, explaining why Ammonite doesn't march in formation with its Sednoid siblings. The stellar flyby hypothesis has gained considerable traction among astronomers who find Planet 9's requirements increasingly difficult to satisfy. Computer simulations show that a single close encounter with a passing star could scatter dozens of objects into Sednoid-like orbits, creating exactly the kind of mixed population that observations now reveal. Unlike the Planet 9 scenario, which demands ongoing gravitational shepherding over billions of years, stellar encounters provide a one-time catastrophic explanation that naturally produces orbital diversity. But perhaps the most radical alternative involves rogue planets, massive worlds that were born in our solar system but later ejected into the cosmic wilderness. During the chaotic early period of planetary formation, gravitational interactions between giant planets could have flung one or more Neptune-sized worlds into interstellar space, but not before these departing planets scattered objects into extreme orbits during their final death spiral out of the system. This rogue planet scenario has a certain poetic justice to it. Instead of an invisible planet that continues to lurk in the outer darkness, influencing objects through subtle gravitational whispers, we have a dramatic story of planetary exile. The missing planet hypothesis suggests that our solar system once hosted additional worlds that paid the ultimate price for gravitational instability, leaving behind only scattered survivors to testify to their former existence. The evidence for such planetary ejections isn't purely theoretical. Observations of other stellar systems reveal numerous examples of rogue planets, massive worlds wandering through interstellar space without any parent star to call home. Our own solar system's architecture, with its unusually compact arrangement of giant planets, suggests that significant reshuffling occurred during the early epochs of planetary formation. Recent computer simulations exploring the rogue planet hypothesis have produced surprisingly detailed predictions about what such ejection events would leave behind. The timing, direction, and orbital characteristics of scattered objects would all bear the fingerprints of the departing planet's final gravitational tantrum. Researchers are now comparing these theoretical signatures with the observed properties of Sednoids, looking for clues about whether our solar system once hosted additional worlds. The debate over Sednoid formation mechanisms reflects a broader challenge in planetary science. How do you reconstruct ancient events from fragmentary evidence scattered across billions of years? It's like trying to solve a cosmic murder mystery where the crime scene has been thoroughly cleaned. The witnesses have mostly disappeared, and the only remaining clues are a few suspicious orbital trajectories floating in the outer darkness. Each Sednoid discovery adds another piece to this cosmic puzzle, but the picture that emerges grows more complex rather than clearer. Ammonite's orbital characteristics suggest one type of formation mechanism, while the clustering of the other three Sednoids points towards something entirely different. Either multiple processes operated simultaneously during the early solar system's evolution, or our understanding of gravitational dynamics in the outer solar system remains fundamentally incomplete. The technical challenges of studying these ancient survivors continue to push astronomical instrumentation to its limits. Detecting objects like Ammonite requires not just powerful telescopes but also sophisticated data analysis techniques capable of identifying incredibly faint moving targets against the stellar background. The process resembles searching for cosmic needles in an astronomical haystack, except the needles are moving and the haystack spans billions of cubic astronomical units. Modern Sednoid hunting relies heavily on automated survey systems that can compare millions of images, flagging anything that moves between observations taken weeks or months apart. These digital detective systems must distinguish genuine moving objects from cosmic ray hits, satellite trails, and various instrumental artifacts that can masquerade as distant worlds. It's a testament to both human ingenuity and computer processing power that we can reliably detect objects as faint and distant as Ammonite at all. The fossil survey that discovered Ammonite represents the cutting edge of this technological archaeology. Using the Subaru telescope's massive field of view, the project systematically scans predetermined regions of sky where theoretical models predict ancient survivors might lurk. Each observation session produces gigabytes of data that must be carefully processed to extract the subtle signals of distant worlds creeping across the cosmic background. This systematic approach has revealed something unexpected about the outer solar system's demographics. Rather than finding a handful of isolated survivors scattered randomly through space, surveys are uncovering evidence for a surprisingly rich population of these ancient objects. Current estimates suggest that hundreds, perhaps thousands, of Sednoid-sized bodies remain hidden in the cosmic darkness, waiting for sufficiently sensitive surveys to reveal their presence. The statistical implications of this hidden population add another layer of complexity to theories about Sednoid formation. If hundreds of these objects exist, then the apparent clustering of the first three discovered might indeed represent a genuine gravitational signature rather than mere coincidence. But if the population is truly diverse, with objects like Ammonite following independent orbital paths, then the clustering might simply reflect observational bias in the early days of Sednoid hunting. Resolving this statistical puzzle requires discovering many more of these distant wanderers, a task that will likely occupy astronomers for decades to come. Each new find either strengthens or weakens the case for various formation mechanisms, gradually building a more complete picture of how these extreme orbits came to exist. It's a slow process of cosmic detective work, assembling clues scattered across billions of years and billions of miles. The upcoming Vera Rubin Observatory promises to revolutionize this field by conducting the most comprehensive survey of moving objects ever attempted. Over its planned 10-year mission, the facility will repeatedly image the entire southern sky, creating a detailed movie of everything that moves against the stellar background. This unprecedented dataset should reveal hundreds of new trans-Neptunian objects, including many additional Sednoids that will either vindicate or demolish current theories about their origins. The anticipation surrounding Rubin Observatory's first light reflects the high stakes involved in understanding our solar system's most distant residents. If the facility discovers dozens of new Sednoids, all showing orbital clustering consistent with Planet 9's influence, it would provide compelling evidence for the hidden planet's existence. But if the new discoveries reveal a diverse population of orbital orientations, similar to Ammonite's independent path, it would deal a potentially fatal blow to the Planet 9 hypothesis. Meanwhile, alternative detection strategies are being developed to search for Planet 9 directly, rather than inferring its presence from orbital clustering. These efforts face enormous technical challenges, as the hypothetical planet would appear incredibly faint even to the most powerful telescopes currently available. The search resembles looking for a black cat in a dark room while wearing sunglasses, except the room is several billion miles across and the cat might not actually exist. Advanced computational techniques are being employed to predict where Planet 9 might appear in the sky based on the gravitational effects it should produce on known objects. These theoretical treasure maps guide observational searches, focusing scarce telescope time on regions where the invisible planet is most likely to reveal itself. It's a calculated gamble, investing enormous resources in the search for something that might be nothing more than a theoretical phantom. The broader implications of the Planet 9 debate extend far beyond our own solar system. Understanding how extreme orbits form in planetary systems has direct relevance for interpreting observations of exoplanetary systems, many of which show evidence for planets on highly eccentric or widely separated orbits. The mechanisms that shaped our own solar system's architecture likely operated in stellar systems throughout the galaxy, making Sednoids like Ammonite cosmic Rosetta Stones for understanding planetary formation in general. Recent discoveries of exoplanets on extremely distant orbits around other stars suggest that our solar system's complement of remote objects might not be unusual at all. Many stellar systems appear to host populations of widely separated planets and smaller bodies, indicating that the processes responsible for creating extreme orbits operate commonly throughout the galaxy. Understanding these mechanisms in our own cosmic backyard provides crucial insights for interpreting observations of more distant systems. The study of Sednoids also connects to broader questions about the solar system's place within the galactic environment. Our sun's motion through the Milky Way exposes the outer regions of the planetary system to various external influences, from passing stars to giant molecular clouds that could gravitationally perturb distant objects. These galactic effects operate on timescales of millions to billions of years, potentially explaining some aspects of Sednoid orbital evolution that purely internal mechanisms cannot address. Computer simulations exploring these galactic influences reveal a complex interplay between internal solar system dynamics and external perturbations from the broader galactic environment. The outer regions of planetary systems exist at the interface between these two realms, subject to gravitational influences from both their parent star's planetary system and the surrounding galactic neighborhood. Understanding this cosmic borderland requires considering processes operating across an enormous range of spatial and temporal scales. The discovery of Ammonite thus represents more than just another entry in the catalogue of distant solar system objects. It's a key piece of evidence in ongoing efforts to understand how planetary systems evolve over cosmic time, how they interact with their galactic environment, and how the gravitational chaos of their youth leaves permanent scars in the form of extreme orbital populations. Each new Sednoid discovery adds to this growing body of evidence, gradually illuminating processes that operated billions of years ago in the darkness beyond Neptune. As we peer deeper into the outer solar system with increasingly sophisticated surveys and telescopes, we're essentially conducting an archaeological expedition through cosmic time. The objects we discover are artifacts from an ancient era, when our solar system was young, violent, and still settling into the relatively stable configuration we observe today. Like terrestrial archaeologists piecing together ancient civilizations from scattered pottery shards and foundation stones, astronomers are reconstructing the solar system's tumultuous youth from the orbital fragments that survived the gravitational upheavals of planetary formation. This archaeological perspective makes every new discovery precious, and Ammonite's story grows even more fascinating when we consider what it tells us about the ancient solar system's hidden violence. Computer simulations tracking the object's orbital history reveal something remarkable about the timing of cosmic events. Roughly 4.2 billion years ago, all known Sednoids, including our rebellious Ammonite, followed paths that were surprisingly similar. This primordial alignment suggests that whatever sculpted these extreme orbits operated during a specific window in the early solar system, like a cosmic construction crew that showed up, rearranged the outer neighborhoods, and then vanished into the night. But here's where the plot thickens like cosmic gravy. If all these objects started with similar orbits billions of years ago, why do they look so different today? It's as if you had four dancers who began performing the same choreography, but over time, three of them kept dancing in sync, while the fourth wandered off to perform an entirely different routine. Something caused this orbital divergence, and understanding what that something was could unlock secrets about forces that shaped our cosmic neighborhood when it was young and chaotic. The leading candidates for this ancient disruption read like a cast of gravitational villains from a cosmic thriller. First, there's the stellar interloper scenario, where a massive star wandered too close to our young solar system during its birth within a crowded stellar nursery. Picture the early solar system as a delicate mobile hanging above a cosmic crib, with all the pieces balanced just so. Now imagine a giant hand reaching in and giving it a violent shake. That's essentially what a stellar flyby could accomplish, flinging objects into the extreme orbits we observe today while leaving others relatively undisturbed. The mathematics of stellar encounters reveal their incredible destructive potential. A single star passing within a few hundred astronomical units of the young sun could gravitationally scatter thousands of objects, creating a population of survivors with diverse orbital characteristics. Unlike the Planet 9 hypothesis, which requires ongoing shepherding over billions of years, stellar flybys provide a one-time catastrophic explanation that naturally produces the kind of orbital diversity that Ammonite represents. Then there's the rogue planet hypothesis, perhaps the most dramatic explanation of all. This scenario suggests that our solar system once hosted additional giant planets that were later ejected through gravitational warfare among the developing worlds. Imagine a cosmic game of musical chairs where there weren't enough stable orbits for all the players. The losers would be flung into interstellar space, but not before their final death spiral scattered objects like Ammonite into the extreme orbits we observe today. The evidence for such planetary ejections isn't purely theoretical. Astronomers have discovered numerous rogue planets wandering through interstellar space, massive worlds that were cast out from their birth systems to wander the galaxy alone. Our own solar system's unusually compact arrangement of giant planets suggests that significant reshuffling occurred during the early epochs of planetary formation. Perhaps we're looking at the survivors of a much more crowded and chaotic early system. What makes the rogue planet scenario particularly intriguing is its ability to explain both the ancient clustering and the current diversity of Sednoid orbits. A departing planet could initially scatter objects into similar orbits through its gravitational influence, but over billions of years, subtle perturbations from the remaining planets and external forces would gradually spread these orbits apart. It's like watching ripples in a cosmic pond slowly disperse over geological time. Recent computer simulations exploring this possibility have produced surprisingly detailed predictions. The timing, direction, and orbital characteristics of scattered objects would all bear the fingerprints of the departed planet's final gravitational tantrum. Researchers are now comparing these theoretical signatures with the observed properties of Sednoids, looking for evidence of ancient planetary exile written in the language of orbital mechanics. But perhaps the most unsettling possibility is that multiple mechanisms operated simultaneously during the solar system's youth. Rather than seeking a single explanation for Sednoid formation, we might need to accept that our cosmic neighborhood experienced a perfect storm of gravitational chaos. Stellar encounters, planetary ejections, and other violent processes could have all contributed to sculpting the population of extreme objects we observe today. This multi-mechanism approach would explain why some Sednoids like Sedna, 2012 VP113 and Leleaku Honua show orbital clustering, while others like Ammonite march to their own gravitational drummer. Different objects could have been affected by different processes, creating a mixed population that reflects the varied catastrophes of the early solar system. It's a humbling thought that our current cosmic tranquility might be built on the gravitational bones of ancient chaos. The technical challenges of testing these competing theories push astronomical detective work to its absolute limits. Unlike experiments in terrestrial laboratories, astronomers can't manipulate cosmic variables or replay ancient events to see what happens. Instead, they must piece together evidence from fragmentary clues scattered across billions of years and billions of miles. like forensic investigators working a cosmic cold case where most of the evidence has been destroyed by time. Each new Sednoid discovery becomes a crucial piece of this ancient puzzle. The object's orbital characteristics, estimated size, and probable composition all provide clues about the forces that shaped its path through space. But interpreting these clues requires sophisticated computer models that simulate billions of years of gravitational evolution, tracking how different formation mechanisms would affect orbital distributions over cosmic time. The computational demands of such simulations are staggering. Modeling the gravitational interactions between multiple planets, thousands of small bodies, and occasional stellar intruders requires supercomputers running for weeks or months to trace the evolution of a single scenario. These digital time machines allow researchers to test whether proposed formation mechanisms could actually produce the orbital characteristics we observe in real Sednoids. But even the most sophisticated simulations come with built-in limitations. They must make assumptions about initial conditions in the early solar system, the frequency and characteristics of stellar encounters, and the properties of planets that might have been ejected billions of years ago. Each assumption introduces uncertainty into the results, making it challenging to definitively prove or disprove any particular formation mechanism. This uncertainty is both frustrating and exciting for researchers studying these ancient objects. On one hand, it means that definitive answers about Sednoid formation remain tantalizingly out of reach despite decades of intensive study. On the other hand, it suggests that major discoveries still await, hidden in the orbital characteristics of objects yet to be found or in theoretical insights that haven't yet been developed. The ongoing debate over Planet 9 exemplifies this scientific uncertainty. Despite nearly a decade of intensive searching since the hypothesis was first proposed, the supposed planet remains stubbornly invisible. Some researchers interpret this absence as evidence that Planet 9 doesn't exist, while others argue that it simply means the planet is smaller, more distant, or located in a different part of the sky than originally predicted. The controversy has sparked increasingly creative detection strategies. Some teams are using machine learning algorithms to analyze vast datasets of astronomical images, searching for subtle patterns that might reveal Planet 9's gravitational influence. Others are developing new theoretical models that predict where the planet should appear based on its supposed effects on known objects. It's a high-stakes game of cosmic hide-and-seek where the prize could be the discovery of a new world in our own solar system. Meanwhile, alternative explanations for the apparent clustering of extreme trans-Neptunian objects continue to gain ground. Statistical analyses suggest that the clustering might be less significant than originally thought, possibly arising from observational biases or the small sample size of known objects. As more distant objects are discovered, the apparent clustering could dissolve like a mirage, taking the primary evidence for Planet 9 with it. The discovery of Ammonite adds fuel to this fire by demonstrating that not all extreme objects follow the predicted patterns of planetary shepherding. Its orbital independence suggests that whatever forces shape the outer solar system were more complex and diverse than a single massive planet could provide. Each additional discovery that doesn't fit the Planet 9 model weakens the case for the hidden world's existence. But the absence of Planet 9 wouldn't necessarily solve the mystery of Sednoid formation. Even if the hypothetical ninth planet proves to be a theoretical phantom, astronomers would still need to explain how objects like Ammonite acquired their extreme orbits. The stellar encounter and rogue planet hypotheses would remain viable alternatives, each with their own strengths and weaknesses in explaining the observed population of distant objects. The resolution of this scientific puzzle will likely require a combination of new discoveries and theoretical insights. The upcoming Vera Rubin Observatory promises to dramatically expand the census of distant objects, potentially revealing hundreds of new Sednoids over the next decade. This flood of new data will either vindicate existing theories or force astronomers to develop entirely new explanations for the architecture of the outer solar system. The broader implications extend far beyond our own cosmic neighborhood. Understanding how extreme orbits form in planetary systems has direct relevance for interpreting observations of exoplanetary systems throughout the galaxy. Many of these distant systems show evidence for planets on highly eccentric or widely separated orbits, suggesting that the processes responsible for creating extreme orbits operate commonly throughout the universe. Recent discoveries of exoplanets on extraordinarily distant orbits around other stars indicate that our solar system's population of remote objects might be quite typical. The mechanisms that scattered Ammonite and its siblings into their current orbits likely operated in stellar systems across the galaxy, making these ancient survivors cosmic ambassadors from a universal process of planetary system evolution. The study of Sednoids also connects to fundamental questions about the solar system's interaction with its galactic environment. Our Sun's journey through the Milky Way exposes the outer regions of the planetary system to various external influences, from encounters with other stars to passage through giant molecular clouds that could gravitationally disturb distant objects. These galactic effects operate on timescales comparable to the age of the solar system itself, potentially explaining aspects of Sednoid orbital evolution that internal mechanisms alone cannot address. Computer simulations exploring these galactic influences reveal a complex dance between internal solar system dynamics and external perturbations from the broader cosmic environment. The outer regions of planetary systems exist at the boundary between these two realms, subject to gravitational influences from both their parent star's retinue of planets and the surrounding galactic neighborhood. Understanding this cosmic frontier requires considering processes operating across an enormous range of spatial and temporal scales. The challenges of studying such remote objects continue to drive innovations in astronomical technology and technique. Modern Sednoid hunting relies on automated survey systems capable of processing millions of images, sophisticated algorithms that can distinguish genuine moving objects from various artifacts, and statistical methods that can extract meaningful patterns from small samples of extremely diverse objects. These technological advances have revealed that the outer solar system is far more populated and dynamic than previously imagined. Rather than a sparse collection of isolated objects drifting through empty space, the region beyond Neptune appears to harbour a rich ecosystem of ancient survivors, each carrying information about the gravitational catastrophes that shaped our cosmic neighbourhood billions of years ago. The discovery rate of these distant objects continues to accelerate as survey capabilities improve. Each new find adds another data point to the growing database of extreme orbits, gradually illuminating the processes that operated during the solar system's violent youth. It's a slow process of cosmic archaeology, assembling evidence from scattered survivors to reconstruct events that occurred in the darkness beyond Neptune, when the Earth was young and the solar system was still finding its gravitational balance. As we stand on the threshold of a new era in solar system exploration, with powerful new telescopes coming online and sophisticated surveys beginning their systematic mapping of the outer darkness, the story of objects like Ammonite represents just the beginning of a much larger narrative. These ancient wanderers are cosmic time capsules, preserving information about conditions and processes that would otherwise be lost forever to the passage of billions of years. The questions they raise about planetary formation, gravitational dynamics, and the evolution of orbital architectures touch on some of the most fundamental issues in astronomy. How do planetary systems form and evolve? What role do external influences play in shaping their long-term development? How common are the processes that created our own solar system's unique characteristics? Each Sednoid discovery brings us closer to answering these cosmic questions, but also reveals new layers of complexity in the gravitational tapestry that connects our local planetary system to the broader galactic environment. The dance between theory and observation continues, with each new piece of evidence either supporting or challenging our current understanding of how worlds are born, evolve, and occasionally meet violent ends in the darkness between the stars. The implications of Ammonite's discovery ripple outward like gravitational waves through the astronomical community, touching everything from our understanding of planetary formation to the very methods we use to search for hidden worlds. But perhaps the most profound impact lies in what this ancient wanderer tells us about the nature of scientific discovery itself, and how a single unexpected observation can transform decades of carefully constructed theory into cosmic rubble. Consider the psychological journey that astronomers have travelled since Planet 9 first captured imaginations in 2016. For nearly a decade, researchers have invested countless hours in theoretical modelling, observational campaigns and computer simulations, all built on the foundation that a massive hidden planet lurks in the outer darkness. Graduate students have written dissertations about it, conferences have been organised around it, and funding agencies have supported searches for it. The hypothesis became more than just a scientific theory. It became a shared dream of discovery that united astronomers around the world. Now comes Ammonite, this cosmic troublemaker that refuses to follow the script. Its orbital rebellion doesn't just challenge a theory. It challenges the emotional investment that the astronomical community has made in that theory. It's like spending years planning the perfect surprise party only to discover that the guest of honour might not actually exist. The disappointment is real, but so is the excitement of realising that the universe still has the power to surprise us. This emotional dimension of scientific discovery often gets overlooked in the sterile language of academic papers and conference presentations. Behind every hypothesis lies human curiosity, ambition, and yes, attachment to ideas that feel particularly elegant or satisfying. Planet 9 possessed exactly this kind of appeal. It offered a simple, beautiful explanation for complex observations, the kind of theoretical elegance that makes scientists' hearts sing. The idea that a single massive world could orchestrate the dance of distant objects across billions of years had an almost poetic quality that transcended mere mathematical modelling. But science, at its core, is a process of creative destruction. New observations constantly challenge existing ideas, forcing researchers to abandon cherished theories in favour of better explanations that account for all available evidence. This process can be painful, particularly when years of work suddenly seem to point in the wrong direction. Yet it's also profoundly exciting, because it means we're learning something genuinely new about the universe. The story of Ammonite and Planet 9 illustrates this scientific evolution in real time. We're witnessing the messy, uncertain process by which human understanding advances, complete with false starts, competing interpretations, and the gradual accumulation of evidence that slowly tips the scales toward new conclusions. It's democracy in action at the cosmic scale, where observations vote on the validity of theories and no amount of theoretical elegance can overcome contradictory evidence. The technical challenges of studying objects like Ammonite also reveal something profound about the limits of human knowledge and the ingenuity required to push beyond those limits. These ancient wanderers exist at the very edge of our observational capabilities, so faint and distant that detecting them at all represents a triumph of technology and human persistence. Each observation requires perfect conditions, sophisticated instruments, and months of careful data analysis to extract meaningful signals from cosmic noise. The process resembles digital archaeology, sifting through millions of pixels to find the handful that contain evidence of distant worlds. Automated algorithms scan vast databases of images, flagging anything that moves against the stellar background with the patience of electronic monks devoted to cosmic contemplation. It's a testament to both human creativity and computational power that we can reliably detect objects as remote and faint as Ammonite in the first place. But detection is only the beginning of the challenge. Once found, these objects must be studied with techniques that push observational astronomy to its absolute limits. Determining basic properties like size, composition, and orbital characteristics requires combining observations from multiple telescopes over extended periods, building up a composite picture, pixel by pixel, and measurement by measurement. It's like trying to understand a distant city by catching occasional glimpses through a keyhole during brief moments when the lighting is just right. The statistical aspects of Sednoid science add another layer of complexity to an already challenging field. With only 4 confirmed members of this exclusive club, researchers are essentially trying to understand a population from a sample size that would make any statistician nervous. Every new discovery carries enormous weight because it represents a significant fraction of the known population. Ammonite alone increased the Sednoid sample by 25%, fundamentally altering the statistical landscape of theories about their formation. This small sample problem pervades much of outer solar system research. Unlike studies of stars or galaxies, where researchers can analyze thousands or millions of objects to identify meaningful patterns, Sednoid science operates in a regime of small numbers where individual discoveries can overturn entire theoretical frameworks. It's like trying to understand human behavior by observing only 4 people, then having your conclusions dramatically altered when the 5th person does something completely unexpected. The challenge becomes even more acute when considering observational biases that affect which objects we're most likely to discover. Current surveys are most sensitive to Sednoids when they're near perihelion, the closest point in their orbits to the Sun. This creates a natural bias toward finding objects during specific phases of their orbital cycles, potentially skewing our understanding of the population as a whole. It's like trying to understand traffic patterns by only observing intersections during rush hour. Future survey programs promise to address some of these limitations through systematic, long-term monitoring of large areas of sky. The Vera Rubin Observatory, in particular, will repeatedly image the same regions over its 10-year mission, creating detailed movies of everything that moves against the stellar background. This temporal coverage will reveal objects at all phases of their orbits, providing a more complete picture of the distant population. But even with dramatically improved surveys, the fundamental challenge of small numbers will persist for years to come. Sednoids orbit so slowly that their discovery rate will likely remain limited by the patience required to track their glacial motion across the sky. Unlike asteroids that zip around their orbits in a few years, these ancient wanderers take millennia to complete single circuits of the Sun. Building a statistically robust sample will require decades of sustained observation and the kind of scientific patience that spans entire careers. The international nature of Sednoid research reflects both the technical challenges involved and the collaborative spirit that drives modern astronomy. The fossil survey that discovered Ammonite brings together researchers from Japan, Taiwan, and other countries, combining expertise in instrumentation, data analysis, and theoretical modeling. The Subaru telescope itself represents a triumph of international cooperation, funded by Japan, but located in Hawaii and used by astronomers from around the world. This collaborative approach extends to the theoretical work as well. Computer simulations exploring different formation mechanisms draw on expertise from planetary dynamics, stellar evolution, and galactic astronomy. Understanding how Sednoids acquired their extreme orbits requires considering processes operating across an enormous range of scales, from the detailed gravitational interactions between individual objects to the large-scale structure of the galaxy itself. The computational demands of such work push the boundaries of available technology. Modeling the evolution of the outer solar system over billions of years requires tracking the gravitational interactions of thousands of objects while accounting for external perturbations from passing stars and galactic tides. These simulations consume enormous amounts of computer time, running on supercomputers for weeks or months to trace the evolution of single scenarios. But even the most sophisticated simulations come with built-in limitations that reflect our incomplete understanding of initial conditions in the early solar system. How many objects originally populated the outer regions? What was their size distribution? How frequently did other stars pass close enough to gravitationally disturb the developing system? Each assumption introduces uncertainty into the results, making it challenging to definitively prove or disprove any particular formation mechanism. This uncertainty creates both frustration and opportunity for researchers studying these ancient objects. On one hand, definitive answers about Sednoid formation remain tantalizingly out of reach despite decades of intensive study. On the other hand, the persistence of fundamental mysteries suggests that major discoveries still await, hidden in the orbital characteristics of objects yet to be found or in theoretical insights that haven't yet been developed. The broader implications of Sednoid research extend far beyond our own solar system to questions about planetary formation throughout the galaxy. The mechanisms that scattered these objects into extreme orbits likely operated in stellar systems across the Milky Way, making Sednoids like Ammonite cosmic ambassadors from universal processes of planetary evolution. Understanding how they formed provides crucial insights for interpreting observations of exoplanetary systems, many of which show evidence for planets on highly eccentric or widely separated orbits. Recent discoveries of exoplanets on extraordinarily distant orbits around other stars suggest that our solar system's population of remote objects might be quite typical rather than exceptional. The gravitational chaos that characterized our cosmic neighborhood's youth appears to be a common feature of planetary system evolution, repeated countless times throughout the galaxy's history. This universality makes the study of local Sednoids relevant for understanding planetary formation in the broadest possible context. The connection between local and galactic processes adds another dimension to Sednoid science. Our solar system doesn't exist in isolation, but rather travels through the Milky Way, experiencing a constantly changing galactic environment over cosmic time. Encounters with other stars, passages through spiral arms, and interactions with giant molecular clouds all leave their mark on the outer regions of planetary systems. Understanding these external influences requires considering our solar system as part of a much larger cosmic ecosystem. The timing of various galactic influences adds complexity to theories about Sednoid formation. Different external perturbations operate on different timescales, from individual stellar encounters lasting a few million years to the solar system's orbital motion around the galactic center, with a period of roughly 200 million years. Disentangling these various influences requires careful analysis of how different processes would affect orbital evolution over billions of years. Computer simulations exploring galactic influences on the outer solar system reveal a rich tapestry of interactions between internal dynamics and external perturbations. The results suggest that the current population of extreme objects reflects not just the initial conditions of planetary formation, but also the accumulated effects of 4.5 billion years of galactic evolution. It's like studying the rings of an ancient tree, where each layer records the environmental conditions of a particular epoch. This long-term perspective transforms our view of objects like Ammonite from simple curiosities to cosmic archives that preserve information about conditions throughout solar system history. Their orbits encode not just the gravitational chaos of planetary formation, but also the subtle influences of stellar encounters, galactic tides, and other external forces that have shaped our cosmic neighborhood over geological time. The archaeological metaphor becomes even more apt when considering the preservation of information in orbital characteristics. Unlike physical artifacts that decay over time, orbital elements can remain stable for billions of years, faithfully recording the gravitational events that created them. Sednoids like Ammonite are essentially fossils made of mathematics, their orbital parameters serving as permanent records of ancient catastrophes. But reading these mathematical fossils requires sophisticated theoretical tools and computational techniques that continue to evolve as our understanding improves. Each new discovery provides additional constraints on formation models, gradually narrowing the range of viable explanations for how these extreme orbits came to exist. It's a slow process of elimination, ruling out mechanisms that can't explain all available observations, while refining those that remain consistent with the evidence. The iterative nature of this process reflects the broader rhythm of scientific discovery, where new observations constantly challenge existing theories and force researchers to refine or abandon their models. The cycle of hypothesis, prediction, observation, and revision continues indefinitely, gradually building a more complete and accurate understanding of natural phenomena. In the case of Sednoids, we're currently in the early stages of this cycle, with fundamental questions about formation mechanisms still unresolved. The discovery of Ammonite represents a crucial data point in this ongoing process, but it's far from the final word on Sednoid formation. Future discoveries will either support or challenge the implications of its orbital independence, gradually building a more complete picture of the distant population. Each new find carries the potential to confirm existing theories or send them tumbling into the dustbin of scientific history. This uncertainty keeps the field vibrant and exciting, attracting researchers who thrive on the challenge of solving cosmic puzzles with limited data. The combination of observational difficulty, theoretical complexity, and fundamental importance ensures that Sednoid research will remain at the forefront of solar system studies for decades to come. Every clear night at major observatories around the world, astronomers continue the patient work of scanning the outer darkness for additional members of this exclusive club. The emotional journey of discovery in Sednoid science mirrors the broader human experience of exploration and understanding. Each new object found represents a small victory against the vast darkness that surrounds us, a successful attempt to push back the boundaries of the unknown. The excitement of discovery, the frustration of limited data, and the satisfaction of gradually building understanding all reflect the fundamentally human drive to comprehend our place in the cosmos. As we stand at the threshold of a new era in solar system exploration, with powerful new telescopes coming online and sophisticated surveys beginning their systematic mapping of the outer darkness, objects like Ammonite serve as guides to a much larger story waiting to be told. These ancient wanderers are cosmic breadcrumbs, leading us deeper into the mysteries of planetary formation and the violent processes that shaped our cosmic neighborhood when the solar system was young. The questions they raise touch on some of the most fundamental issues in astronomy and planetary science. How do planetary systems form and evolve? What role do external influences play in shaping their long-term development? How common are the processes that created our own solar system's unique characteristics? The answers lie hidden in the orbital mathematics of distant objects, waiting for patient observers to decode their ancient messages. Each Sednoid discovery brings us closer to understanding these cosmic questions, but also reveals new layers of complexity in the gravitational symphony that governs planetary motion. The dance between theory and observation continues, with each new piece of evidence either supporting or challenging our current understanding of how worlds are born, evolve, and occasionally meet dramatic fates in the darkness between the stars. The story of Ammonite and its impact on the Planet 9 hypothesis exemplifies this ongoing scientific adventure. What began as an elegant theoretical explanation for orbital clustering has evolved into a more complex and nuanced understanding of the forces that shape the outer solar system. Whether Planet 9 ultimately proves real or remains forever theoretical, the search for it has already revolutionized our understanding of the distant reaches of our cosmic neighborhood. And somewhere in the outer darkness, Ammonite continues its ancient journey, oblivious to the scientific revolution its discovery has sparked. This cosmic time capsule from the solar system's violent youth carries secrets about gravitational catastrophes that occurred billions of years ago when our planetary system was still finding its balance, and the Earth was nothing more than a molten ball of rock orbiting a young and restless star. The mathematics of its orbit whisper stories of stellar encounters, planetary migrations, and gravitational chaos that shape the architecture we observe today. These whispers grow louder with each new discovery, each additional Sednoid that adds its voice to the cosmic chorus telling the tale of our solar system's tumultuous past, and the forces that continue to shape its evolution across the vast expanses of space and time.